This is tutorial 4B, question 5A. In this question, we are asked to find the response to an input which is a complex exponential given the system transfer function Hs equals to this s plus 6 divided by s squared plus 5s plus 6. The input is this complex exponential e minus, or I should say e st, where s is equals to minus 0.4 plus j4. You can then think of it as e minus 0.4t multiplied by e j4t. So we have a decaying function and we have a complex exponential rotating. You can express it in also this form where ej4t expressed as cosine 4t plus j sine 4t, and hence you can then plot the real part and the imaginary part of xt. The dotted line here that you see is e minus 0.4t. In this expression, it is a everlasting complex exponential going from minus infinity to infinity, positive infinity. And in this case, the theory tells us that the output to a complex exponential, everlasting complex exponential, is the complex exponential, which is this value here, multiplied by the transfer function evaluated at S0, where in S0 in this case is the S0 in the expression over here, which is minus 0.4 plus j4. In another chapter of the lecture, we have shown that Hs0 is called the frequency response of the system, and the frequency response of the system evaluated at S0 can be used to multiply by the eigenfunction Es0 to produce the output. So this is this colored box here stating this fact. We'll just use this theory, and therefore our problem now is to evaluate what is Hs0. This is S0. S0 came from exactly this expression here, E S0t. So S0 is equals to minus 0.4 plus j4. We substitute this value into the various s's. So you'll see that I've highlighted the various s's, and when we finish evaluating, out comes a complex number in rectangular form, and then we convert it into the polar form or the complex exponential form, showing the magnitude and the phase. This magnitude and the phase is exactly Hs0 over here, and we can use that to multiply by the original signal Es0t. So let's substitute. This is Hs0, and this is the input signal x of t. Now, because they are complex exponential, we can start to move this expression around. So the a comes to here. Let's call this the a, the gain at S0. Here is the phase shift. The phase shift is moved into the complex exponential term here. E minus 0.4 is here, which is this expression. And now we have the final answer. Yt is equals to 0.3348 e minus 0.4t times the complex exponential with omega equals to 4 and the phase shift equals to minus 1.5645, which was gotten by this here. Of course, you can then express this as the real part and the imaginary part, and then you can plot the real part and the imaginary part over here. The blue and the green are the real and imaginary part of yt. You can now compare this against this, and you will see that originally the input is about 1 at time 0, and now at time 0 it is 0, so there's a phase shift and it has become smaller. Look at the blue one. Because the gain is 0.3348, means that it has multiplied by the original signal and he has scaled it down to 0.3348. Additionally, it has introduced a phase shift of minus 1.564. Thank you.